Welcome to the Explainer. Today, we are cracking the code on one of Python's, well, one of its most confusing errors. If you've ever written a function inside another function and tried to change a variable, I bet you've hit this wall. Well, today, we're going to tear that wall right down. All right, let's kick things off with a little mystery. Take a look at this code. It's a simple counter, right? It's supposed to return another function that just increments a number. It looks like it should work perfectly. But nope. When you run it, it just crashes with that dreaded unbound local error. So, what gives? So to solve this puzzle, we're going to peel back the layers of Python's scope rules, kind of like an onion. We'll look at that deceptive error, talk about the local scope rule, see how to reach for global variables, and then, of course, find the non-local solution. We'll even cover some surprising quirks before we wrap it all up with the 4 big scope laws. Okay, first up, the deceptive error. Let's really dive into this thing. It's one of those errors that gets everybody, beginners, pros, you name it, because honestly, it just seems to defy logic when you first see it. So here it is. The interpreter complains that the local variable num was referenced before it was assigned. But wait a second, you and I can both see it. Num equals 0 is sitting right there in the outer function. So why on earth is Python telling us it can't find num inside the incrementer? What is actually going on here? Okay, so the key to this entire mystery, the whole thing, it comes down to one simple but really powerful rule that Python follows the second it looks at the code inside any function. And this is the crucial point, right here. The moment Python's compiler scans your code and sees an assignment, something like num plus equals 1, inside that incrementer function, it makes a snap decision. It says, aha, you're assigning to num in here, so num must be a local variable. And here's the kicker. That decision applies to the entire function, from the very first line to the last. And that right there perfectly illustrates the problem. See, num plus 1 isn't just one step, it's really 2. First, Python has to read the current value of num, then it can add 1 and assign it back. But remember that snap decision? Python already decided num is a local variable. So it goes looking for a local num to read, and comes up empty. It hasn't been given a value locally yet. And that's exactly why we get that referenced before assignment error. So how do we break out of this local box? Well, our first tool for doing that is the global keyword. This is what you reach for when you want to modify a variable that lives way out at the top level of your script. Think of the global keyword like a special key you give your function. It's you explicitly telling Python, hey, see this variable x? Don't you dare create a new local one. I want you to reach all the way out to the main top-level scope and mess with the x you find there. And you can see the difference clear as day here. On the left, without global, our function just creates its own little private x. Inside, x is by, but the original outer x, still high, totally untouched. But on the right, bam, we use global, and that gives the function permission to reach out and permanently change that top-level x to by. Now, global is powerful, for sure. But for our original counter problem, it's kind of like using a sledgehammer to crack a nut. It reaches way too far. We don't want to modify a variable at the tippy-top level. We just want to modify the one in the function right outside us. And for that, we need its much more precise cousin, nonlocal. Yeah, nonlocal is the perfect tool for the job when you're dealing with nested functions. It basically tells Python, hey, for this variable, don't look here locally, and don't go all the way out to the global scope either. Just look in the next function that's wrapping me. It's super specific, really targeted. And there it is, the solution to our original puzzle. Just by adding that one simple line, nonlocal num, we've given our incrementer function the permission it needed. We've told it, go ahead, reach into the counter function scope and modify its num. And just like that, the error vanishes. Our counter works exactly like we wanted it to from the start. All right, so we've got the main rules down pat, but Python, like any good language, has some weird and wonderful corners. So let's explore a couple of little quirks that can trip up even the pros. Okay, pop quiz time. Check this out. We've got a global variable named A. We also have a class variable, also named A, inside this Fred class. Now the function E is defined inside the class. So my question for you is, when we call Fred.E of it, which A is it going to find and print? Is it global or class? The answer, believe it or not, is global. I know it's weird, right? And the reason comes straight from Python's design documents. It turns out that when a function that's inside a class goes looking for a variable, it doesn't actually look in the class scope around it. It just skips the class definition entirely and looks in the next enclosing function scope. And in this case, that happens to be the global scope. Oh, and get this. It's not just the equals sign, the assignment operator, that makes a variable local. The del command, the one that removes a variable, is also considered what's called a binding occurrence. So what does that mean? It means if you just try to del x inside a function, Python will assume x is a local variable, and you'll get that same unbound local error if you haven't given it a value first. Crazy, right? Okay, let's pull all of this together into one simple ultimate rulebook. This is the exact four-step process that the Python interpreter follows every single time it needs to figure out what a variable's value is. It's called the LEGB rule, and the order is everything. First, Python checks the local scope, right inside the current function. If it's not there, it checks the enclosing scopes, any functions that are wrapped around the current one moving outwards. Still no luck, it checks the global, top-level scope. And if all else fails, it finally checks the built-in scope for things like the print function. And here's the key. The very first place it finds a match, it stops looking and uses that value. So now you have this mental model, right? You've got LEGB, you've got nonlocal and global in your toolbox. And the big takeaway here isn't just about squashing bugs. It's about being able to structure your code with intention. When you know exactly where your data lives and how your functions can talk to it, you can build programs that are way more predictable, easier to read, and just more robust. So the real question is, how are you going to use this knowledge to write better, cleaner code?